Right now we're going to look at how to implement some code in MATLAB in order to execute a Kalman filter. It's actually very straightforward to do this, to convert the filter steps to MATLAB, because MATLAB automatically works with matrices and vectors directly. The most tricky part, I think, is taking care to synchronize all of the time indices of all of your variables, and that's why the program loop that I drew in the previous topic can be a helpful reference, so that you know in what order do you do the steps and where do you make the measurements and all of that. We are going to look at code for a Kalman filter, but we're also we need truth data on which, or at least measured data on which to implement the Kalman filter. So we need to have the filter, but we also need to have the system. In real life, the system is provided. It's the battery cell, and we're taking measurements of voltage and current. But in our simulation, we don't have, in this case, measurements of voltage and current, and so we have to simulate the true system alongside simulating the Kalman filter. So really we have some system, I've got an input, I've got an output, and then on the side I've got the Kalman filter operating as the picture to have in mind. So the code is going to have Kalman filter steps, but also system simulation steps. Because we're simulating the true system, we need to be able to come up with random values for process noise and sensor noise. And that is, we need to be able to, at least in general, have the ability to compute random values, random variables that are not zero mean in general, and have a Gaussian distribution, and have a specified covariance matrix. So I'm using Y here as a generic symbol for that, but we're thinking of the process noise W and the sensor noise V specifically. Using our notation for a Gaussian, we want to be able to create random samples of the random variable Y, where Y is distributed according to a normal distribution with mean Y bar and covariance sigma Y tilde. Well, if you look around MATLAB a bit, you'll see that MATLAB has a Gaussian random number generator, rand_n, but that random number generator gives us X output, if you will, that has zero mean and has uncorrelated components, and the variance of each component is 1. And we'd like to be able to come up with a transformation, so I use rand_n, it gives me X, and I convert X into Y having those properties. It's quite simple to do this once you see the trick. What we do is we say, let little y, a sample of y, be Y bar to change the mean, and then A transpose times X. Now, it's not the system A matrix. This is a different A matrix here. And so what we're doing, without looking at A specifically, is we're taking the X components, which are identically distributed with zero mean and identity covariance, and we are multiplying by A, which doesn't change the mean, but it does change the covariance, and then we're adding Y bar, which does change the mean, but does not change the covariance. So independently, we're fixing both things that we need to fix. The issue is, what is A? And A turns out to be a square matrix with the same dimension as sigma Y, and we need this relationship here to be true, that A transpose A equals sigma Y tilde, and then you can actually figure out what is the expected value of Y. Well, it turns out it's Y bar. What is the expected value of Y times Y transpose? Well, it turns out that I need A transpose to be sigma Y in order for this to work, because this is actually just A transpose times A is what we get there. Okay, so if A transpose A equals sigma Y, how do we do that? There's a linear algebra technique called the Cholesky decomposition that returns exactly what we want. And here's a snip of MATLAB code that can do this. So suppose I want a random variable with mean 1 in the first component and 2 in the second component, and a covariance matrix of 1, 0.5, 0.51. And we accomplish that by saying, okay, A equals the Cholesky decomposition of this covariance matrix. X, in this case, I am making a single random vector, 2 tall, 1 wide, and Y then is simply Y bar plus A transpose times X. And that gives me a single sample Y with the correct mean and covariance. The Cholesky decomposition works if your desired covariance matrix is positive definite, but it does not work if it's positive semi-definite. And there's a different decomposition, an LDL decomposition that could be used in that case. And it's a little less numerically efficient usually, but we can do this. And that code also works. Now in this code, I'm actually doing 5,000 random variables at once. Here I'm doing 2, 1. Notice here I'm doing 2, 5,000. And I could have done 2, 5,000 here. So I would have 5,000 random vectors, each 2 tall, and they would all end up having the right characteristics when I do this operation. So that could work. Here's a plot. Either way, if I use Cholesky or the LDL decomposition, I get a scatter plot of all the data points, and you can kind of visualize the mean is around there maybe. There. So 1, 2, yep, that's probably about right. And the covariance in MATLAB, you can actually use the var command on your scatter data to get an estimate of the covariance, and it is in fact correct in this case, within numeric error probably. So why do we do that? We need to simulate the real system. The real system has noise. In our final battery management system application, we don't have to simulate the noise. We never do these random numbers because the noise is added by nature for us. We don't have to do that. But for the simulation here, we do. Okay, without further ado, let's have a look at some MATLAB code to implement a linear Kalman filter. The model that we're simulating in this example is actually given after the code. Let me skip ahead just so you see it, and then we'll come back. We are simulating in this code, although the code is general, but I'm simulating new state equals 1 times old state plus 1 times input plus 1 times W. Output Y equals 1 times X plus 0 times U plus V. So A equals 1, B equals 1, C equals 1, D equals 0 in this example. And in this example, we've also chosen to have sigma W and sigma V both be equal to 1. But the code, again, can handle a more general case than that. So I start out the code by setting sigma W to whatever it is. In this case, we said it was 1. Sigma V to whatever it is, in this case 1, A, B, C, and D to whatever they are, and I define a variable called max iter, which is the number of iterations or time steps that I want this Kalman filter to operate. And you might just want it to be indefinite in an application. Here I wanted to do it for some short amount of time so we could plot results and have a look at them. I need to keep track of the true system and my estimator. So x true is the true system that I'm simulating, and x hat is my estimator state. I'm going to assume perfect knowledge of the state of the true system to begin with and see how that evolves over time. And the initial input, U0, we will assume is 0 because we just don't know what it is. And whatever it did happen to be, we hope the common filter converges to it anyway over time. I leave some, I reserve some storage space for variables. If you have a vector in MATLAB that changes dimension inside of a loop, every time you change dimension, the operating system has to get rid of the old memory, get new memory, and it's a very slow process. So if we get one chunk of memory first for the entire variable and then simply write to the variable in the loop, it's a lot faster. Here I'm creating storage for the true state of the system, and I'm initializing it to 0 to be whatever height x true is. In this case it's just a scalar, and then however many iterations. And then the first location I am setting to x true, and then I will update that in the program loop as time goes on. I also reserve space for the estimate in the same way, and I reserve space for the covariance of the estimate. In this case, if x is 5 long, my covariance is a 5 by 5 matrix, so I need 25 locations, or in general the length of x squared locations at every iteration to store that matrix. Everything is initialized and it's time to jump into the program loop right here. So k is my time index, and I am beginning with step 1a. I start with x hat. Now the interpretation of x hat there is this is x hat k minus 1 plus, because I haven't changed x hat yet. So it's still whatever it was at the end of the last time through the loop. So this is going to be x hat 0 plus at this point in time. So a times x hat plus added to b times u, well, this is going to be uk minus 1. It's whatever u was whenever we finished the loop at the last point in time, and this is u0 right now. And I am computing that and assigning it to x hat. So this is x hat k minus. And you'll notice I use the same name. I have, at the beginning of the loop, I overwrite the previous estimate with my new prediction, and at the end of the loop, I overwrite that prediction with the new estimate. And so the same variable holds the prediction or the estimate depending on where you are in the program loop. This is part of what I mean by you have to be careful to keep things straight so you're not using the wrong variable at the wrong time step. Step 1b, similarly, this here is going to be sigma x tilde k minus 1 plus, because I haven't updated anything yet. And I multiply by a and by a transpose, and I add sigma w, and I assign it to the same variable, but it now has a new meaning. This is going to be sigma x tilde k minus. So I take the previous estimated covariance, and I turn it into the present prediction error covariance. At this point, although I could no, this is when I have to do it. I simulate. Remember, this would not be in a common filter we implement on a real system, because I don't simulate the real system, I measure the real system, but here I am simulating the truth. So one thing I need is to know what is the deterministic input to the system, and just for fun, this is what I decided the deterministic input would be, but that was just a choice. It could be anything. And I said, well, let's have a cosine with some noise on it be the driving input. But don't let the noise fool you. The noise is measured, so I actually know u exactly later on in the common filter. So in a real system, I would measure u because I need to use u later on. But I would not compute the state of the real system. Similarly, in the simulation, I have to create the process noise and the sensor noise, and that's what I'm doing here using the trick we saw on the prior page of the Cholesky decomposition in order to find the appropriate scaling matrix and multiplying that by random numbers of the right size. Gaussian random numbers are the right size, and I add 0 because it's 0 mean. So the true output, the measured output of the system, which also I would have in real life, I would measure that, I'd measure u and y, is c times x plus d times u plus the sensor noise v, and all of these for time index k, and this here x true, I'm pre-computing xk plus 1 is a times xk plus b times uk plus wk there. Again, trying to keep the indices right, you actually have to, at this point, compute what the next state is rather than computing what the present state is. That had to be computed already in order to do this. Now I'm ready for Kalman filter step 1c, which is I compute the output prediction y hat equals c times the state prediction right now, x hat plus d times u. I measured u right there. Step 2a, I compute the Kalman filter gain matrix, which is c times sigma x times c transpose plus sigma v. That's my sigma y first. And then L equals sigma x times c transpose times the inverse of sigma y. And in MATLAB, this is the efficient way to do the inverse, multiply by the inverse of a matrix. It uses back substitution, I think, to do it in a way that's numerically sound and faster than inverting a matrix first and then multiplying. Kalman filter step 2b, the estimate x hat plus equals the prediction x hat minus plus L times y true minus y hat. And again, at this point, I am taking my x hat k minus and converting it into x hat k plus. I use the same variable name, but it now has a different meaning from now on in the loop. It's now the estimate and not the prediction any longer. And similarly, the sigma x tilde k minus becomes a sigma x tilde k plus by subtracting L times sigma y times L transpose. And that's the end of the computations. Now I need to store some information. I store the true system state for plotting. Normally I wouldn't have that, but I do because I'm simulating the true system. I store the x hat for plotting, and I store, notice what this does is it takes the square matrix and it converts it into a vector by putting column 1 in first, and then column 2, and then column 3, etc. It columnarizes the result. Then I loop. I just do that over and over again until max iterations have been simulated, and I plot some things here. Now the plotting code, I believe, has to be modified slightly. If I have a vector state, I'll let you figure out how to do that. I have to vectorize my sigma in order to do that properly. But in any case, this is roughly what you want to do in the vector case, and it is what you want to do when your state is a scalar like we have here. So I'm plotting the true state, the estimated state, and then the estimated state plus 3 times square root of the covariance, and then minus, so plus 3 standard deviations minus 3 standard deviations in order to get error bounds. It's also, that's the state, and it's also nice to have estimation errors plotted because I think sometimes that can help us visualize better. And that is x minus x hat is the estimation error, and the error bounds, the estimation error on average is 0. So it's 0 plus 3 and 0 minus 3 times sigma are plotted as the bounds. When I run this code, I get different results every time because different random numbers happen every time, but this is what happened one time when I ran it, and you can copy and paste the code yourself. In fact, I hope you do. That's one way to learn and see it run many times. On the left-hand side, we see the state of the system versus iteration, and the state is the solid line, the estimate of the state is the blue dotted line, and the estimation bounds are the purple dotted lines. And we see that the truth and the estimate are never exactly the same, but they're roughly in the same ballpark. And even better news is that the estimate bounds always contain the true state. So if I rely on the estimate being within bounds, I'm going to be okay for doing any kind of predictions or use cases for some application of this model, the estimate in some, however you want to use it. On the right-hand side, we plot the estimation error with the estimation error bounds, and we see again, maybe a little bit easier, that the estimation error is generally within plus minus 2, and it's always within the error bounds, and we would expect it to be within the error bounds about 99.7% of the time. So that's not a surprise, but it tells us that things are working according to theory. So that is MATLAB code, and I wanted to show that to you because I wanted you to see that the Kalman filter itself is about one screenful of code, less than one screenful of code. Because here is step 1A at the top, 1B, 1C, 1D, 2A, 2B, and 2C. It's literally, in this case, the way I did it, it's 7 lines of code. You could do it in 6 lines if you wanted to be pedantic by plugging that in there and that in there and not creating the intermediate variable sigma y to do that calculation. So this is not very difficult to implement, especially in MATLAB, and implementing in some other language like C is a little bit more difficult only because C does not have matrix operations built in, and you would have to write your own matrix multiplies and inverses. But besides that, it's not difficult to implement this Kalman filter. So that brings us to the end of our linear Kalman filter discussion. I would like to spend one more section talking about some practical considerations. I have a course on Kalman filtering because it's been my experience that even though a Kalman filter is, like I said, here it is, there's your filter, it should be simple enough that I could just make a toolbox, a Kalman filter toolbox, and then anyone could download that toolbox and just apply it to their application, whatever that might be, and it would just work. My experience is that's not true. There's always some real-life issue that crops in, and you need to tweak a thing here or a thing there, especially with the nonlinear Kalman filters, in order to make the overall scheme robust. So I'd like to look at some practical considerations in the next section, and that will very naturally lead us into a discussion of nonlinear Kalman filtering, which is what we do after that.